Good morning, chemists, or whatever time of day it is you're watching this. This video is going to be our first one on radicals. So let me go to our radical handout. Okay. All right. So this is a brand new chapter. Radical handout. It's kind of long, like all of mine are, but um, let's talk about the handout format. So please let me know if you'd rather have the bigger pages, with the big spaces that I always had. But so far, I'm kind of liking the handout where we can just go to the whiteboard, but holler, send me a message or something if you'd rather have the big, large ones. Okay, the radicals. What in the world is a radical and why do we care? All right, so a radical, remember, is an unpaired electron. So it is made by homolytic cleavage of a bond, which means one electron will go into each location. So remember, the radicals, they don't make charged species. They're not going to make ions. They're going to make just unpaired electrons. Now, unpaired electrons, as we learned in Gen Chem, is very unfavorable. And so they are highly reactive. Okay, they do not like to stick around. They go and they react with whatever they touch. It is sp2 hybridized. So remember, there is, and then woo, in the beginning, so they're flat. Okay, just like a carbocation. And they do not rearrange though. So for instance, if I make this radical right here, this primary radical, it's in an sp2 hybridized orbital, but it does not rearrange to go and make the secondary radical. That's the nice thing. They don't just swap. But the bad thing is they're so reactive that you would probably get that product anyway. All right, how are we going to determine their energies? So we're going to use something called their dissociation energy. And so it's very similar to the delta H that we've talked about, but they are labeled DH because it's the dissociation energy, and they're specifically talking about radicals. But keep in mind, they are very similar to carbocations. So this little generic right here, allylic, tertiary, secondary, primary, methyl. Now, I give you a pretty long table right here. The reason for that is when I was going through learning about radicals, the stability seemed to stymie me. Like, wait a second, I thought it was the other way, and it makes perfect sense. But of course, I was talking myself in circles. So I gave you a whole bunch of numbers, and we're going to go and figure out these trends together. All right, so question number 1. Determine the energy trends and the stability for each of the families. So the HX family, we'll put an HF right here. We will put an H. You know what? That's writing awfully big. Let's see if I can write a little smaller. HF, HCl, HBr, HI. All right, so let's go up here and let's get some numbers. All right, so HF is 569 and then 431. So 569, 431. And I'm peeking over at my answer key so I don't have to keep scrolling up there. 366 and 297. All right, that's great. We can get those numbers off the chart, but how do we interpret them? Let me go back really quick up here. The weaker the bond, the more stable the radical. Okay, so the weaker the bond, the more stable the radical. All right, so 297 is the weakest, so HI in this family must be the most stable. Okay, so there's one trend that we know. So HF is less than HCl, which is less than HBr, which is less than HI. All right, so let's do the next trend. What about our halogens? Now, remember, halogens, fluorine is notorious. So we're going to put a little F2 and then Cl2, Br2, Cl2, Br2, I2. All right, again, I'm going to go up there and I'm going to grab these numbers off the chart. This one is 159. This one is 243, 192, and 150. All right, again, when we're dealing with the numbers, the weaker the bond, the more stable the radical. All right, and I really am going to go and talk about that again in a minute because it's very, very important to get that relationship between reactivity and stability. But let's finish this one. All right, so F2, Cl2, Br2, and I2. If you'll notice, let me change colors. This poor little F that it doesn't match the trend. So generally, when we talk about halogenation, did you recognize I never used fluorine in the past because fluorine just isn't a world by itself. So let's make a trend from the others and then kind of insert the fluorine. All right, so 151 is the lowest energy, so it's the most stable. So iodine is better than bromine, which is better than chlorine. But this poor fluorine is clear down there with iodine. All right, which again is not unexpected. Fluorine's just kind of a weird species. So we're going to go Cl2 is less than Br2, which is less than I2. And I am not going to put fluorine into that trend, but that is the trend of the other for the rest of the family. All right. What about the degree of stability? What kind of stability am I talking about? Well, we have talked about, carbocations, and I like to go through the whole gambit. So benzylic, allylic, tertiary, secondary, primary, and methyl. All right, so I need to know there's my benzylic, there's my allylic, tertiary, secondary, primary, methyl. All right, so we're going to go up here and I ask for this in two different ways. One of them is just ripping off a hydrogen, and one of them is ripping off a carbon. So we're going to do the hydrogens first. So we should be right here. Okay, so if you'll notice, I underlined that hydrogen. So that's the number I'm going to use. So there's the methyl, there's the primary, there's the secondary, there's the tertiary. This is the allylic, and that one should be benzylic. Okay, so those are the numbers that I'm grabbing. All right, so it looks like I have a 356. I have oh look, a 356. A 381. A 395. A 410. And I didn't write down methyl. Methyl is 439. All right, again, the weakest bond is the most stable. And so benzylic and allylic, in this case, are identical, which is just a little bit better than tertiary, which is a little better than secondary, a little better than primary, which is better than methyl. Okay, so there's our other trend. Does it make sense? And for the same reason as carbocations, their radicals have stability because the electron donating groups, the more carbons there are to help out the radical formation, the more stable it is. All right, so that looks perfectly like carbocations. But my next question is, what if I remove a carbon? So this one specifically was only removing a hydrogen to get that radical. What if I actually broke a carbon-carbon bond to make that radical? So let's try it again. So again, let's go benzylic. Okay, so I'm actually going to end up with a carbon radical as well. And it will be the same for all of them. And the question is, really, would that make a difference? Well, let's see. All right, again, I'm going to go back to my numbers here. I should do it in a different color. We're going to do blue this time. All right, so this time I am removing a carbon, so right here. So this whole thing would be removed. This whole thing would be removed, okay, rather than the hydrogen. Allylic and benzylic right there. So there's the numbers I'm grabbing. And I have 301. And oh, look, 301. I'm going to erase that just so it doesn't look like I'm putting the methyl in the middle. All right, my tertiary is going to be 335 and 351 and 356 and 368. Now again, not going to be surprised about this trend. Okay, these two are equal, which is better than tertiary, which is better than secondary, better than primary, better than methyl. But the real question is, why are they different? Okay, what's the difference overall when you break off a carbon instead of a hydrogen? All right, well, let's ask ourselves the question. What are the numbers saying to us? And in this case, 301 is lower than 356. So it is more stable, or we get a more stable radical by ripping off the methyl group. Interesting. Interesting. Now, again, we're not going to be going into radicals so much that we're going to have to nitpick, but it's the trends that are really, really important. Now, another trend, and I should have put it on here, I'm going to make a note to myself to go back and do this, is what about, hybridization? Oh, you're welcome. I put that on here too. All right. So if you'll notice, we already have a primary, or sorry, a sp3, different color. Let's see what purple. Yeah. All right. So this one right here is an sp2. We need an sp3. And we'll just take, we don't want the benzylic, just a generic sp3. Okay. All right. I put sp3. That's sp. Said one thing, wrote down another. All right. What are my trends here? And since it's right here, I'll just put these numbers. So sp3, sp2, sp. Okay, my sp3 was 410. My sp2 was 452. And my sp is 523. Very interesting. Very interesting trend, because for carbocations, the more S character you had, the more stable. But I'm not trying to stabilize a charge here. I'm trying to stabilize a radical. So in this case, sp3 is more stable than sp2, which is more stable than sp. And we can jump through this whole table looking at things. I am going to come back to these three here at the bottom. Okay. There's going to be some interesting things going on with those. All right. I should have put right here, let me see, A, B, C, D. So let's put that as an E choice. And E should be the hybridization trend. All right, so we have answered all those. Now, I left you some questions to do on your own. Hey, using the bond dissociation energies, can you tell me the difference between HF and I2? Well, again, we'll go grab those numbers, and the lower number will be the more stable. All right, and question number 3. Create a radical for each type of hydrogen and determine which would be the most stable. So we're going to do one of those together. All right, let's just, you know what, let me just draw the hydrogens. Okay, so these two are identical. Okay, so this one and this one are identical. So there's 1, 2, 3. There are 4 types of hydrogens. So how many different types of radicals should I show? Well, 4 types, and it doesn't matter where you start. So let's rip off that one, that one, that one, and either one of those two. Okay, let's talk about stability. This is a primary. This one is a secondary. This one is a tertiary. And this one is back to a primary. All right, now I'm not having you put them in order. Is there a difference between those two primaries? I'm just asking, hey, which would be the most stable? And the tertiary in this case would win. All right. And so for all of those, rip off every unique type of hydrogen and just do a compare and contrast. Get just used to the stability of the different radicals. Back up to this page. So in a nutshell, radicals is a lone electron. Very similar to carbocations, but there's just a few differences, mostly in that hybridization question. But you can trust your instincts for the stability to match that of carbocations. Just remember, yes, they are sp2 hybridized. That'll play into stereochemistry. They're very short-lived. They're very highly reactive. They do not rearrange. And the weaker the bond, the more stable the radical. Because if it doesn't take very much energy to break that bond, then that radical isn't desperate to put the bond back. Okay, so that's kind of the mantra that I always used in the back of my mind. If it's not desperate to put it back, then that bond must have been weak in the first place. All right, and that is the first video in our wonderful little series of radicals. Until next time, jolly out.